Hi everybody, this is Mr. Lee, and in this video we are going to go over centripetal forces. Alright, let's begin. So, the definition of centripetal is center seeking, and this is important because it's going to help us actually create our free body diagrams and our net force formulas. And centripetal forces are forces that point along the center axis, and it causes the object to move in a circle. So the important distinction here is that the objects for centripetal motion problems are objects that are moving along a circular path. Okay, so this is kind of like if you were to run around on a track. This is not the same as the object spinning in place. Okay, so we call those rotational problems. Alrighty, so we are doing objects that are moving in a circular path. Okay, the other distinction I need to point out is that centripetal forces are not centrifugal forces. In fact, you'll never hear me talk about centrifugal force. Because centrifugal forces are not real, it's what we call a illusionary force. Okay, now this is a pretty tricky idea because many people believe that centrifugal forces are real, but it's actually a illusion. Okay, we feel, and I put feel in quotes because, when we are, let's say, driving and there's a roundabout and you are going in a roundabout, or if you're making a left-hand or right-hand turn, our body would feel the centrifugal force, but there's actually nothing there to cause that sensation. It's a reactionary force. All right? So let's begin. The best way to approach this is by looking at an example. So in this example, I'm going to bring back up the bowling ball activity that we did at the beginning of the unit. So let's say there's a top-down view of a bowling ball and it's moving in a straight line. Okay. In order to make the ball move in a circle, you have to push the ball towards the middle. So let's start off with that. I'm going to just move this here. We have a bowling ball, so it's important here we're looking at the top-down view. Okay, the bowling ball, let's say, is moving up this way. So this is a object in motion that stays in motion, so it's just moving in a straight path. All right, now we get to a point where we want the bowling ball to no longer go in a straight path, but to now move in a circular path, like so. So if we want the ball to go in a circular path, like so, there's certain conditions that must be met when we interact with the ball. So the first turn that we're going to make when the ball is here is we have to push the ball towards the middle. So I'm going to show that with this. So I'm going to say this is our first push. Now, if we take a look here, okay, here I want us to indicate the tangential velocity. So tangential velocity, or VT, is the velocity of object at the moment of time, and it is always going to be perpendicular to the circle. Okay, so at this point, at that exact moment right there, the object is actually moving forward, and I'm going to indicate this in blue. So here, this is our VT. Now, it's important to know that you are not allowed to have velocity vectors on your free body diagram, right? So this is just our way of setting up the problem so that we can create the net force formula. If this were a free body diagram problem for an FRQ, you would just have that F. All right. So we have this tangential velocity going that way, and we're pushing the bowling ball to the right. So I can actually draw this all throughout the circle as long as I follow this rule. It has to be perpendicular to the circle. So meaning, if I no longer push on the ball, the tangential velocity is the path that the ball will take. So if I do not push the ball to the right, in this instance here, the ball will continue to move in a straight line. So let's take a look here. All right, at that point right there, if I stop pushing on the ball would just move straight to the right this way. But if I keep on pushing the ball, okay, I would have to keep on pushing the ball towards the middle. Okay, now what about, let's say, right here? So at the point, that's like a 1 o'clock or 2 o'clock, okay, the tangential velocity will look like this. And in order for the ball to be moving in a circle, I'm once again pushing towards the middle of the circle. Okay, so what you're seeing is how the tangential velocity and the centripetal forces are always going to be lining up. Your net centripetal force will always be perpendicular to the tangential velocity. The tangential velocity is always going to be perpendicular to the circle, and the forces will always point towards the middle. Okay, at this point, I want to also indicate that because force is also taking a look at the acceleration, okay, the acceleration is also pointed along the middle as well. Now, it's important to point out definitions of acceleration. We know that acceleration, we can look at an object that is speeding up. Okay, you can look at an object that is slowing down, and we're going to add to this definition is a changing of direction. And so what we're seeing here is the changing of directions. So once again, let's go back to the car analogy. Speeding up, this is the gas pedal. Okay, slowing down, these are the brakes. And the changing of direction, this is actually your steering wheel. All right, so this is covering point 1. Okay, we would draw the free body diagram normally. So this is the forces that point towards the middle is like you pushing on the broom, or excuse me, you with the broom pushing the ball towards the middle. Now here's the other important thing. Any force that's pointing towards the middle is considered to be positive. Okay, and let's just take a look at a example here. So all of these forces that I drew are to be considered to be positive forces. Now, it's important to point out that we're looking at different moments of time. So here, this could be t0, here, this could be t2, here, this could be t3. Okay, so whenever we do a free body diagram, we're only choosing one moment of time. So we could be doing a free body diagram for t2. So if we're doing a free body diagram for t2, okay, where this is the path of the circle, we would say that this is our F. And here's the important distinction. Because this is the middle of the circle, okay, this force is considered to be a positive force. Yes, even though it's pointing downwards, because we're looking at centripetal motion problems, anything that points towards the middle of the circle is considered to be positive, and any force that's pointing, let's say, away from the circle, so let's call this F2, okay, this F2 would be considered to be negative. So now the next point is what this necessarily means. So the idea is the centripetal forces are all the forces that cause the object to move in this circular path. So let's take a look at T2 here as I erase that. So if I look at T2, okay, we are pushing the ball towards the middle of the circle there with our broomstick. And let's say force of friction exists. Let's do force of friction here. Let's say the force of friction is pointing this way. Okay, so the idea is that the push that we are exerting on the ball with a broomstick is actually causing it to move in a circle. But you see this force of friction here? Because this force of friction is not along what we call the centripetal axis, this force of friction is not doing anything to cause the ball to move in the drawn circle. So now let's talk about this idea of centripetal axis and problem-solving strategies. Whenever I do these problems, okay, I draw the circle and I draw the free body diagram and I make it a point. I make it a point to highlight the centripetal axis. So all that means is that you go from the middle of the circle and you go right to the object. Okay, you go up and down. So anything that's along this axis is considered to be a centripetal axis. Now, notice I'm not saying this is the y-axis or the x-axis, but the centripetal axis. So what this means is that any force along this highlighted axis is considered to be a force that will help this rotational or this circular moving object. Notice that this F of F is not along that highlighted path, therefore that force of friction has nothing to do with the motion of the circle. Okay, now let's say there was another force, right? And let's say this force is pointing this way. We'll call this one F2. So this is as if, right, so you're pushing the bowling ball towards the middle of the circle, but let's say you have a partner that's pushing the ball away from the middle of the circle. Okay, this F2, because it's not pointing towards the middle of the circle, remember, center seeking, this F2 is considered to be negative in our formula, whereas this F is considered to be positive. So we've been talking about this net force formula, so let's actually write this net force formula down. So the formula for centripetal motion is the same as Newton's second law. F is equal to ma. But this is where subscript come into play. If we're looking at centripetal axes, or circular motion objects, we put a C there for centripetal and a C there for centripetal. Okay, let's do the left hand side first. So if I'm taking a look at this axis here, I see that we have positive F, positive because it's pointing towards the middle of the circle, and then here we have this negative f2. That negative f2 because it's pointing away from the circle. Okay. Now I wrote this up here in my notes, but if at any point this negative f2 becomes greater than that f here, what happens is that this circular path that we just drew in there will cease to exist, because this f2 will overpower the regular f force. So in that case, if that happens, a new path or new circular path will be taken by the object. Okay, so the force that is greatest and is pointing towards the middle of the circle causes the object to move in that circle. All right, so I'm going to get rid of that circle there. All right, now this brings us to the rest of the formula. Mass is just mass. By the way, this is your official formula. Okay, right there. The f and f minus 2, that's like problem dependent. Okay, and here we have a brand new variable, a of c. So acceleration is the changing of velocity. So in order to show a change of velocity when we are looking at direction, we have a brand new formula. I'll put this formula in parentheses. This is on your formula sheet. It is the tangential velocity squared divided by the radius, or how far you are away from the middle of the circle. And so for this problem here, this would be the formula that I would use in order to solve for whatever variable that we're looking for. Okay. Once again, I want to point out that this force of friction here is nowhere to be found within my formula because it is not along that centripetal axis. All right. Now, there are different ways of finding tangential velocity, and one of the ways I want to point out is that because we are moving in a circular path, and we know that velocity is displacement over time, okay, one of the ways that you can find displacement is by looking at the circumference. So 2 pi r over t also gives you tangential velocity. And this formula, I don't think it's on your formula sheet, so I'm going to put a little star there and say you got to memorize this one. All right. Okay. Let's see. Yeah. Okay. So here's the other thing. Number 4. You are creating a net force formula for the current given circle, meaning that if the F that I drew that's pointing towards the middle circle, if it would change in magnitude. Okay. So let's say the F would get bigger. So if your F gets bigger, then what that would mean is that it would have to adjust the radius of the circle. And let's start with a clean circle here in order to see why that's the case. All right, so here's the circular moving object, right? This is our tangential velocity. I'm actually going to put the tangential velocity off on the side to avoid drawing tangential velocity in a free body diagram, because remember, velocity is not a force. And here we have our F here. All right, so in this case, we have F equals mac, and we just have F is equal to mv squared divided by r. All right, now let's say we increase, right? We increase the amount of force that's causing this object to move in a circle. So if our F goes up, the object itself isn't changing, so this is going to remain constant, and an object in motion stays in motion, right? So that velocity is just going to stay the same velocity. Now what we're looking at is what's happening with this radius. So what we're looking at is a inversely proportional relationship, where if we want our F to increase, our R has to decrease. So if all of a sudden you start pushing on the ball harder, what you're going to get is a tighter circle, okay, or a circle that has a smaller radius. Now, another thing is, as the ball is moving, if you don't push on the ball as hard, okay, so if your F decreases, what happens is your R has to increase because of the inverse proportionality, meaning that you're not pushing the ball hard enough to keep it in the circle that's in black, so that instead what we get is a larger circle there, okay? And so here I'm going to say our R is big because our F is small, and here let's write that our F is big, therefore our R is small, inversely proportional. All right, yeah, so that's the basics behind centripetal motion. At this moment, I'm just gonna do a quick example problem here, okay? And Yeah, let's get to it. So let's say we have a object that's moving in a circle, okay? And let's take a look at the object at that point. And this is what we know of the object. There is a force called F1 here, and let's say there's a force of friction that's pointing in that direction, okay? And let's say, yeah, let's call this F2, and here we have F of 3. All right, and off on the side, I'm just going to write that this is Vt. Now, important to note that velocity is not a force, so it doesn't actually belong on a free body diagram, right? This is just to set up for the net force formula. All right, step 1. So we have our free body diagram-ish, right, with the velocity. I'm going to put a little dot there. Step 1 is to always create your centripetal axis, okay? So anything between the object and this middle of the circle is considered to be the centripetal axes. So you can already see I've highlighted my centripetal forces. Okay, let's set up my formula. So we can say that centripetal forces, we have F1 positive, F2 positive, because it's all pointing towards the middle of the circle, and here we have F3, and that is negative because it's pointing away from the circle. It's equal to mvt squared over r. All right, and so in this example, that's all I would need in order to solve for whatever the problem was asking me to find. All right, on that note, we will get more practice in class, and I'll see you then. Bye-bye.